Hello, my name is Hojun Lee, and I'm an undergraduate student in electrical engineering. Today, I present about this paper, QVECTOR, an algorithm for device-tailored quantum error correction. Real quantum devices are noisy, so we may not able to perform quantum algorithms successfully. So we need a system that can perform quantum operations successfully, even with errors, which is called fault-tolerant quantum computing. To achieve the fault-tolerant quantum computing, quantum error correction is essential. By the quantum threshold theorem, if each element operations like single cubic gauge or CNOT or measurement can be performed with lower error rate than a certain error rate, then the whole error correcting process can achieve an arbitrarily small error rate. However, the problem is that the threshold has not yet been reached, and it's difficult to achieve a sufficient error rate with near-term devices. The surface code that I introduced in the last presentation is the state of art, which requires thousands to 10,000 physical qubits to encode a single logical qubit. So the author tried to reduce error correction overhead via the design of the device-tailored QECC. Let me briefly explain the quantum error correction with simple example, the bit flip code. We can reduce the quantum error with adding some redundancy by letting the logical 0 as 000 state and the logical 1 as 111 state. We can reduce the bit flip error. Suppose that the single qubit bit flip error rate is p. Then by using the bit flip code, we can reduce the error rate to this one, and which is improved when p is less than half. Then let me introduce the QVECTOR algorithm, which stands for quantum variation error corrector. This algorithm is a hybrid quantum classical algorithm which outputs an encoding and recovery circuit and optimizes the parameters of the circuit for the specific quantum device. The encoding circuit consists of a parameter vector P, and it encodes K qubits into N qubits. And the recovery circuit consists of a parameter vector Q and additional R qubits, and it's for recovering errors. They verify the success of the recovery by the average code fidelity. The average code fidelity is defined by the average of the fidelity between the state in the code space and the state after the recovery. The quantum part of this algorithm estimates the average code fidelity of the circuit, and the classical part of the algorithm optimizes the parameters to maximize the average code fidelity. QVECTOR algorithm uses the classical optimizer to optimize the average code fidelity and estimate the average code fidelity with the quantum estimator. And let me explain the average fidelity estimator. First, to get average fidelity, we have to randomly choose the initial logical states. And it can be done by sampling an unitary operator S and applying it to the 0 state. Then use PQC to encode the logical state. And after the noisy process, perform a recovery operation. Since the recovery may not be unitary, we may need the extra refresh qubits. Then decode it. Repeating this process, and the rate of all 0 measurement will be the fidelity. And average with all unitaries S will be the average fidelity. To calculate the average code fidelity, we have to integrate over hard distribution. It's necessary to sample unitary operators on hard distribution to approximate the average code fidelity, but there is an efficient sampling method. We can sample from some small set, which is called a unitary 2 design. Unitary 2 design can mimic the hard distribution up to the second momentum. And the average code fidelity only depends on the second momentum of the distribution. So we can estimate the average code fidelity by sampling from the unitary 2 design. For a single logical qubit case, we only have to consider a unitary S, which makes those 6 quantum states by applying S to the 0 state. And this is the simulation result for the 3-qubit phase damping noise model. For this simulation, they encode a single qubit into 3 qubits, and the phase damping occurs on each physical qubit probabilistically. And the noisy process for each physical qubit consists of these Krong's operators. This is the result of the simulation. The paper compared the average fidelity for 3 cases. The green one is a case with no recovery, where we do not encode and just use a single physical qubit. And the blue one is a case with the Q-vector recovery, and the red one is the optimal one. And they perform the recoveries by 1.8 microseconds. The decay time T1 is 57 microseconds, and the dephasing time T2 is 19 microseconds. And the phase flip probability of the single qubit gate is this. And the phase flip probability of the 2-qubit gate is this. Since the case with no recovery and with recovery has different numbers of the quantum gates, the actual error rates are different. And you can see that Q-vector algorithm almost reaches the optimal recovery, optimal average fidelity, and has much improvement than no recovery case. This simulation used more realistic noise model, the amplitude plus phase damping error model. They encode a single qubit into 5 qubits by using 5-qubit perfect code, and the additional qubit for recovery are unnecessary since we can correct the 5-qubit perfect code with unitary operations. And the Krong's operator for this noisy process is this. They measure the average code fidelity only once and plot it by the wait time. The red one is the numerically optimized result using the iterative semi-definite programming method. And the yellow one is the result of the using 5-qubit code. And blue one is the Q-vector result, which is optimized by the gradient-based optimization. And you can see the Q-vector result outperforms the 5-qubit code when the wait time is longer than 3 microseconds. Pauli twirling approximation is a method of approximating a channel with Pauli terms, and it can be represented like as this, where Pi is an n-fold Pauli operator. The amplitude plus damping noise channel can be represented like this, and after the Pauli twirling approximation, the off-diagonal term like x rho y disappears. They also simulated and compared the exact APD noise model and Pauli twirling approximated APD noise model for 4 schemes. PTA APD noise model can be only achieved 0.904, which is colored with orange, but Q-vector with the exact APD model can outperform it, which is colored with green. So we can say that QVECTOR exploits the Pauli error coherence. And for more than one logical qubit, using approximate unitary 2 design will efficient. We can use following unit cell repeatedly, and the expected deviation, which means the difference with the result simulate with the exact unitary 2 design, is this. In conclusion, QVECTOR algorithm can work on any error models and scalable and more efficient than previous algorithms. And since it used built-in gate to perform a parameterized quantum circuit, it efficiently used the resource. Thank you for listening.
Thank you for the presentation. And any questions?
First of all, thank you for the presentation. I have a question about what is the Pauli enfold operator? How does it work? What the Pauli Crane approximation? Yeah, PI.
PI is a tensor product of n Pauli operators x, y, z, I.
So it's just a Pauli operator. Yeah, what is the n plus n here? In some.
Because it's for n qubit case.
Yeah, fully add.
This one.
Fully add in the signal.
This is a channel. Yes. This is the measurement result, and all zero case, the rate of the all zero case is the average post fidelity, and we optimize the parameters with classical optimization.
Playing these refresh qubits and we have to measure single qubits. 그 채널 교환하는
그 리커버리 할 때 뭐 5 큐빅 코드 같은 경우는 그냥 유니터리 오퍼레이터를 적용해서 바로 1대1 대응시킬 수 있는데, 그렇지 않은 케이스들은 유니터리가 아니라서 저런 게 필요하다고 써 있었어요.
그래서 이제 결과적으로 측정하는 것만 보면 로지컬 큐빅만 측정하면 될 것 같은데 single 큐빅까지 측정하는
잘 모르겠어요. 저도 로지컬에만 있다고 생각했는데 지금 보니까 다르네.
So in the process, we sample from the existing type.
Yes.
And why does it have to be there like a mathematical reason?
The formula of the average fidelity is depends on second momentum. 그래서 저도 약간 보면서 모르겠는 게 있었는데 이 파울리 투어링 어프로시메이션의 의미가 뭔지 잘 모르겠다. 이걸 왜 하는 건지.
말이 뭐라고 백수와 이런 게 없어져서 그냥 쉬워서 하는 것 같아요. Is there any opinion why the people use also the Pauli current expression? Yeah, but I agree with you. Like they already have the exact result, and they use another approximation to show that their algorithm is better. That I thought make a irony. If they only provide the approximate result, then okay, yeah, computational power limits and that they also provide the exact result, and that's in the table below. Yeah, in the okay. Yeah, in the table below, numerically optimized perform better than you apply the exact table.
여기서 말하는 게 코헤런스를 이용했다는 게 신기하다라는 뜻 같은데 원래 계산할 때 PTA를 쓰는 건지 궁금해요. 다른 경우는 뭐 코헤런스를 이용하지 않는 건지.
I don't really get the difference between power and
이런 오프 다이버 텀들 말하는 거니까.
저런 것들은 실제로 맞지 않을 거니까. 근데 이것에 수학적으로는 그게 더 많이 되는데 이제 그 네이버 퀘스천. That is, I think this is a very useful algorithm. So it must be published somewhere. So can I know the reference?
톡방에 올려드릴까? 그 아스프루직 교수님 그 논문이더라고요.
And final question. They compare with optimal is, but what is the standard for optimal? Like,
수학적으로 그냥 진짜 옵티멀한 케이스를 말하는 것 같아. 이거 큐벡터는 알고리즘 써서 최적화한 건데 이거는 실제 해를 말하는 거.
난 조건 안에서
진짜. 네.
is the optimal or we can we use that here too?
Maybe this is just example.
Oh, no, analytical. Okay, any more questions? No?
I think optimal recovery is the analytically analytical solution for this optimization. And QVECTOR recovery is with classical optimization.
So one is using optimizer, the other one is.
A solution. We're doing a solution.
So we're not in the solution because the optimization is hard.
Because it's just a simulation and it
Okay.
checking the performance.
Yeah.
Okay, so if there is no question, thank you for the presentation.